Good afternoon, everyone. Today we'll have a seminar by Dr. Murad Taybjee, our colleague, and he will be giving a talk about singlet fission silicon tandem solar cells. Dr. Murad is ARC Future Fellow and the Senior Lecturer in SPREE, and he's also the Deputy Leader of the Omega Silicon, and his expertise is in spectral management of solar cells, as well as ultra-fast laser spectroscopy. He did his PhD in the same unit, and he has done 2 fellowships, one in UNSW, one in University of Cambridge. And he's now leading the spectrum research team in here, and study the method of solar energy harvesting, as well as renewable energy education. Today he will give us an introduction of the vision of Omega Silicon, which is towards the singlet fission silicon tandem solar cells. And please join me to welcome Dr. Murad, and the floor is yours.
Thanks very much. So today I'm going to be discussing a little bit about what we've been doing at Omega Silicon, and in particular with singlet fission and putting that on a silicon solar cell. But I do realize that we have a pretty mixed audience here, so I'm going to start by doing a little bit of an introduction and give you all a crash course in molecular semiconductors. I'm going to try and give you an undergraduate degree in about 5 minutes. We'll see how we go. And then we'll move into some specific aspects of molecular semiconductors, in particular looking at singlet and triplet excitons, followed by how we can manipulate singlets and triplets in order to drive a process known as singlet fission, which is of course what we've been working on in our group. Finally, how do we take that and then put it onto a photovoltaic device? So that's sort of where I'm going to be taking you today. And the main thing to understand when we're talking about organic semiconductors as opposed to inorganic semiconductors, if there's one key difference, it's the type of excitons that exist in these materials. So in an inorganic semiconductor, you have Vannier type excitons. These are the ones where an electron and a hole, they kind of know they're there, but they don't hang around the same one. They're not monogamous, okay? So what happens is that electron and hole will start to work with other holes in the system. In an organic material, we have what are called Frankel excitons. So if you excite an organic material, the electron knows where the hole is and it stays there. Very few divorces in organic materials. Okay, so just an upshot of this is the fact that for your inorganic semiconductors, you have very weakly bound excitons. That's what I mean when I say they're not monogamous. And in your organic semiconductors, they're very strongly bound. And that also has implications, or actually that arises because you have a high dielectric constant in inorganic semiconductors. All right, so that's why you have this screening between your electron and hole, whereas you have a lower dielectric constant in your organic materials. And that also results in better charge mobility in inorganic devices, in inorganic materials as compared to organic materials. Indeed, the way energy moves around an organic semiconductor is rarely just the charges hopping about, but it's more about the entire exciton jumping from one molecule to the other. So the Frankel exciton sort of jumps about inside your device, and the charges will only separate under certain conditions, okay? So to understand how these materials actually absorb light, I'm going to give you a quick introduction into what we call molecular orbitals. Now, obviously, a molecule has many, many electrons, but we tend to only worry about the electrons that occupy either the HOMO, which is the highest occupied molecular orbital, or the LUMO, which is the lowest unoccupied molecular orbital. And this is a picture of those orbitals for tetracene. And it doesn't really tell you that much, so what I'm going to do is I'm going to just put that to one side and draw an analogy. Okay, so we're going to start to think about something that you may have seen a bit more of, and that's a particle in a box. And we can draw some analogies between a molecule and a particle in a box. So basically, in your particle in a box problem, let's see if I can get this laser pointer to work. and I cannot, so I won't. Here we are. Okay, so in a particle in a box problem, you have basically a very high potential at x equals 0 and a high potential at the length of the box L. And you have these wave functions for your particle in a box. This is like an electron in a potential well. So you have the first wave function, n equals 1, n equals 2, you add another node, n equals 3, you add another node. That is where you pass from positive to negative or negative to positive. And indeed, you can see that here there are more nodes between your red and blue in the LUMO, because you're higher in energy, than in the HOMO. But the analogy doesn't stop there. So you can also, you'll probably recognize that the energy levels are defined, the energy levels are defined by that width of the box. And as your box gets bigger and bigger and bigger, your energy levels get closer and closer together. In the same way for a molecule, as your molecular orbitals get bigger and bigger and bigger, you tend to have a redshift in your molecule. Okay, so you can just sort of imagine that we're really just talking about a particle in a box, and there is a potential barrier between going from one molecule to the next. Okay? Okay, so as I said, chemists worry very little about all the inner electrons. We worry more about what's happening in the highest occupied orbitals and the lowest unoccupied orbitals. So I've got two diagrams here, and they are equivalent. Okay, so on the left-hand side, I have two electrons, with one with spin down and one with spin up in the HOMO. And on the right-hand side, I have what's called a molecular state diagram. So just so you get a good understanding of this, we put electrons into molecular orbitals, but the molecular state is made up of all those electrons being in those orbitals. Okay, so the S0 state, which is our lowest energy state of our molecule, basically tells you that you have two electrons in your HOMO. All right? You can get from the S0 to the S1, create a singlet exciton via absorption. And what happens is you promote an electron from the HOMO into the LUMO, but you retain its spin, and you still have an overall, you got a spin half here and a spin down half here, so you've got an overall spin 0 state there. We can get from a singlet state, the S1, to a lower energy triplet state via a process called intersystem crossing, and that actually involves exactly the same molecular orbitals, but you're just flipping the spin. Now in the molecules that we talk about, basically this is what's called a spin forbidden process. All right, so there isn't a lot of spin orbit coupling. You don't get from the singlet state to the triplet state very quickly. It's a spin forbidden process. And the following diagram is going to tell you a little bit. It's very, very intense, so I'll break it down slowly. The following diagram is going to tell you how do you get from one state to the next. So remember how I said intersystem crossing is spin forbidden? Well, it turns out molecules are quite naughty, and they do forbidden things hundreds of millions of times per second. And intersystem crossing actually does occur quite quickly, but it just gets outcompeted by all the other process. So intersystem crossing from your singlet to your triplets on the order of microseconds, whereas fluorescence from your singlet to the ground state is on the order of nanoseconds. All right? So we can excite our molecule from our S0 state to our S1 state, or we can go from S0 to S2, and that involves taking your electron instead of from your HOMO to your LUMO. You take your electron from your HOMO to your LUMO plus 1. And then these electrons will rattle back down to your S1 state. Sorry, the molecule will rattle down to the S1 state, completely analogous to an inorganic semiconductor, where you excite an electron high in the conduction band, and those electrons rattle down to the conduction band edge. Okay? And this has interesting upshots for the absorption spectrum you get. So you'll notice here that there are all these extra lines drawn on top of this. And that's because our molecule is the thing that's absorbing the light, and inside that molecule, it's going to be vibrating as well. All right? And its vibrations are separate from the neighboring molecule's vibrations. So you can excite your molecule from your ground state to the excited state, but then you can also go up to the excited state plus a vibration. And you can go up +2 and +3 vibrations. These are the phonons inside your molecule. And that manifests itself in your absorption spectrum. So this is the absorption spectrum of tetracene as these different peaks in your S0 to S1 transition. As you get to higher and higher energy, you have the S0 to S2 transition. All right? Similarly, you can get down from S1 to S0 via fluorescence. And that can occur from your lowest vibration to your lowest vibration, giving you your highest transition, and that's that peak here. Or you can go down to the next highest, so you can go down to the lowest state with the vibration, and that's that peak here. So unlike an inorganic semiconductor, your phonon modes are imprinted on top of your absorption and emission spectra. All right, and that's something that's very different for a molecular structures as compared to inorganic structures. But it all arises from the fact that you have these Frankel excitons, and your excitations are really localized, and so are your vibrations. Okay, so we've done molecular orbitals. So that was first year. We've done that. We've done spin. So let's still call that second year. And now we're just going to say, how do we actually manipulate that spin, or what processes can we use that are useful in a device? So I've spent over a decade working on a process called singlet fission. So I'm going to describe what that is on this slide. So we start with all our molecules in our ground state here. We excite one molecule. We have one Frankel exciton sitting in the S1 state. As I said, it's spin forbidden for that S1 to turn into a T1, which I've represented as a blue exciton here. That's spin forbidden, so we're sitting in our S1 state. But if you have two molecules next to each other, we can undergo a process that's called singlet fission, where you generate two triplet excitons on neighboring molecules. Yeah? Now notice that the triplet energy is lower than the singlet energy. There's nothing magic about singlet fission, all right? You still have to conserve energy. But what you've done is you've created two electron hole pairs from a single absorbed photon. And if you can get these triplets to move apart from each other, well then it's a spin forbidden process to get back down to the ground state. So now you have two long-lived excitons from a single absorbed photon. All right, so this is a fast process. In pentacene, it occurs on the order of 80 femtoseconds. In tetracene, 80 picoseconds. And for some other molecules, we can push it out to nanoseconds. But it's a really fast process. And the reason it's fast is because it's spin allowed. Okay, because you can go from your S1 state to two lots of triplets, and triplets have net spin 1. But if you have one triplet with spin 1 here and the other triplet with spin 1 that way, then the triplet-triplet pair state is an overall spin 0 singlet. So it's a spin-allowed process to actually generate, to undergo singlet fission. And that's why it can outcompete fluorescence. And that's why it can be so fast that you actually generate these long-lived excitons. Notice the advantage here over quantum dots that undergo multiple exciton generation. In a quantum dot structure, you can excite very high up, and then you can sometimes produce two excitons from a single absorbed photon. But there's nothing stopping you from going from the higher state to the lower state directly. In a molecular system, you can't go from S1 to T1 very quickly because it's a spin-forbidden process. So by playing around with the spin, we're able to get out these two excitons with, in many systems, 200% yield. Yeah? So we get 200% yield of these excitons of long-lived triplets. I've got two stars there because that is not always true, and we're going to talk about that later on. But there are many, many systems that do this. So the net thing is that we have one photon in and two electron hole pairs out. One thing to keep in mind, of course, as I said, is that this isn't magic. The energy of your singlet state has to be greater than or approximately equal to two lots of the energy of the triplet state, right? So we're not actually increasing any energy here, of course. We're just increasing the number of carriers in the system. All right, so that was third year, and maybe your honors. Let's move on to how will this help photovoltaics? Okay, so I don't really need to tell too many people in the room about this diagram, but I'll just very briefly go into it. All right, if you have a single threshold photovoltaic cell, that is where you only have one absorbing threshold between your valence band and your conduction band. This beautiful work by Louise Hurst and Ned basically was able to show where all that energy, that fraction of incident radiation, where it all goes as a function of band gap. So on our x-axis here, we have band gap, and our y-axis we have the fraction of solar irradiation. So you can see as you go to very, very, very large band gaps, we have a whole lot of our energy is lost to transmission because there's all these photons that have energy less than the band gap. Transmission is not actually the correct word, as I've been told by Ned, but I haven't updated this slide. It should be called below band gap losses, because indeed those photons are actually absorbed. Those low energy photons are absorbed. They just don't produce electrons in the conduction band. So imagine that I didn't say transmission here and that it's just below band gap losses. As you get to very, very low band gaps, well, now you're absorbing most of the solar spectrum, but if you have a band gap of like 0.5 eV, then when a blue photon of 400 nanometers hits your solar cell, or let's say 600 nanometers for an orange one, because I know that that's 2 eV, then you're going to lose at least 1.5 eV off that excess energy above your band gap. And that's what we call thermalization losses. Yeah? In silicon, we sit about here. For a black body radiation, we're at about 30% limiting efficiency for an idealized cell. And you can see that we lose a whole lot of energy to thermalization. And what that means is a lot of our blue photons that are absorbed by our silicon material lose all of that excess energy above the band gap as thermalization, and we're leaving a whole lot of energy on the table. Yeah? So these other losses are a little bit more difficult to explain, so we're not going to go into them. We're just going to deal with this big one here, which is thermalization in our singlet fission solar cell. Okay. Right. So back when I started working on singlet fission in 2009, there was a whole lot of talk of, we're going to use OPV and it's going to be so much cheap because we can print it like newspapers, and we don't need silicon anymore. Like, this will be the next big thing. And then it was very exciting to have singlet fission because you put singlet fission materials, a Frenkel exciton material with another OPV material, and you develop this beautiful OPV singlet fission device, and everything would work really well. Unfortunately, the people working on silicon didn't stop working, so they kept innovating, and the price of silicon we're not going to be able to compete with it in the OPV world. I'm sorry for people researching OPV on the wide scale. All right. So if you can't beat someone, you join them. So what we're going to do is we're going to try and put singlet fission materials on top of silicon. All right. And indeed, if you look at the photovoltaic market, that's where the ITR PV roadmap is suggesting we're going to head. So you can see that these are all the different the cell technologies and their world market share. So you can see that we've had all of these different silicon technologies, PERC, Pearl, PERT, TOPCon in the orange here. Some heterojunction technologies are going to grow in over the next decade, they believe. And if you look up here, this sort of, I don't know, salmon color, I don't know what you call that, maybe beige, that's going to be 5% silicon-based tandems in the next 10 years. Okay? So in 10 years' time, 5% of the market, they think, will be tandems. Singlet fission, if it's going to play a role, needs to work in the next 10 years. All right? And we've got a bunch of different competing technologies, and that's the way this field is going to move forward. But it's definitely going to be something on silicon. It's just working out how that market is going to play out. Right. So this is your solar cell with silicon. It's a very obviously stylized device. You can see that we have all the different colors of the sun being absorbed by your silicon material and generating your Wannier excitons inside your silicon material. And we have a limiting Auger limited efficiency of 29% for silicon. What we want to do at Omega Silicon is put a singlet fission layer on top of the device, right? Notice that the contacts are still on the silicon, not on the singlet fission layer, and we want to generate 2 triplets inside that singlet fission layer for each absorbed photon, funnel those triplets into the silicon layer, and that will allow us to have a limiting efficiency of 42%, right? So now we've increased the ceiling by looking at this device. And you may wonder why it's called Omega Silicon. So we've got this lovely acrostic. Is that what it's called? Anyway, it's organic, multiple exciton generation. Singlet fission is just multiple exciton generation. So we got Omega, and we're of course augmenting silicon. So we are Omega Silicon. Unfortunately, that's also a particular type of watch, which is not great for us, but that's fine. We'll get bigger. Okay, so this was a thermodynamic study I did a little while well, 10 years ago now, which is basically showing where the limiting efficiency for a singlet fission solar cell would lie. On the x-axis, we have the band gap off the bottom cell. So we're really interested in, I guess, silicon here, so around here. And we have a limiting efficiency that's between 40 and 45%. But on the y-axis, there's actually something interesting here. There's an interesting upshot of multiple exciton generation. Since we're absorbing one photon, generating one singlet exciton, and that splits into two excitons, it's actually an entropically favorable process, right? Because you can create two quasi-particles from one quasi-particle. And what that means is that singlet fission can actually occur endothermically. So when I said that the energy of the singlet exciton has to be at least twice the triplet, that was sort of a lie. You can get some thermal energy and actually go uphill. So for instance, in tetracene, which is the fruit fly molecule for singlet fission, it's about 200 millieV endothermic. So actually our limiting efficiency is above that isoenergetic singlet fission effect where your triplets are exactly half the singlet energy. Yeah, so it's actually interesting that we could utilize that entropy to generate a more efficient solar cell. Okay, so that's sort of the whole idea behind this, and we were very lucky to get some ARENA funding for starting this year, where we're looking to develop a singlet fission solar cell. So this was the team of CIs. I'm sorry, the text is quite small, but if you want to look at our names, you can go to this website. And now we've hired some fantastic postdocs, and as well as have some PhD students working on the project. I can assure you that they do indeed have faces, but I just didn't have all their photos. And we also have a whole lot of industry partners helping us out, providing bottom cells so that we can really test out that singlet fission layer. Okay, so by now I hope you understand all of undergraduate chemistry, all of singlet fission, and now I'm going to try and sell Omega Silicon to you. All right. So the main advantages that we have over, other tandem technologies really just lies in this: we have no electric transport in the top cell. We only have excitons hopping about. All right. And what that means is that we can just use an existing silicon device, or most of it, and add a top layer, right? So that's a little bit different to how tandem cells work, where you'd have to contact that second material, that second absorbing material, and that would have to be separately contacted electrically. We don't have to do that. And that means that there's no need to current match. I mean, of course, there are ways around that with a tandem cell if you have a 4-terminal tandem, but we don't even have to think about that. So we have these minimal architecture changes to silicon, and actually, if we use a radiative device, which is one that I'm not going to discuss too much today, but if we use a device that can, in that top layer, harvest the triplet exciton and then emit light instead into silicon, then we can do that completely radiatively, then we don't have to do anything to the silicon device, right? We can just put a layer on top of a silicon device, and that will start to actually have a down converter basically on top of it. Okay? And the nice thing is most of the materials that we're looking at, we get to, like silicon, as silicon progressed, rely on a different industry for their synthesis, because the OLED industry is really gearing up, and so there is a whole lot of these organic optoelectronic materials being developed and being synthesized on larger scales. So that's an exciting aspect of Omega Silicon as well of the technology. Just a quick shout out to my ex-PhD student and current postdoc in the team, Alex, who wrote a review article on the overall state of singlet fission photovoltaics. And if you can't be bothered reading a review article, we also published something in PV Magazine, which is much shorter. So that's sort of where we underline the advantages of Omega Silicon. So the obvious question is, well, why isn't it prevalent? And I suspect it has something to do with timelines. So just as an example, let's take a look at the silicon timeline. Now, 70 years ago, first silicon solar cell was demonstrated in 1953. Some people might recognize this name. Of course, Martin Green started his team in 1974. All right, and out of that, of course, spun out over 90% of current silicon photovoltaic technology from 1983 to 1989. And then we have some very large companies starting up in the early 2000s, gearing up to produce these sorts of modules to get to the ridiculously low prices that we have now. All right, that's a 70-year time window, and it's something that we need to be aware of. So when you're talking about singlet fission, it came up in the literature in 1965 as a way to describe a purely spectroscopic result. This is back when your introductions were, I studied a thing because I wanted to study a thing. When you're writing your papers, it's not about aiming for a technology, and there was just this sort of oddity. You know, singlet fission is a thing that happens, maybe it will happen in other materials. That was the extent of it. In 1979, people who study organic electronics may know the name Dexter. He published a paper where he's like, hey, maybe we could use this in a solar cell, but there weren't any real materials that were being heavily studied for this. And indeed, if you track this onto the silicon roadmap, solar was not really a big thing then, right? So there wasn't a huge amount of work done on PV until the early 2000s. I think I'm missing a little thing here. So in, I think it was about 2006, there was a paper by Hanna and Nozick where they was suggested that singlet fission could be used on silicon PV. So that's, that's that's less than 20 years ago when it starts to be talked about. And again, sorry, they didn't talk about silicon, they talked about an all organic device. So then all of singlet fission research was for all organic silicon PV. I did my little thing here, but we had the first greater than 100% EQE device, but that was all organic, right? So we had all the problems of it being an organic device. And then finally, there was a really big breakthrough in the field back in 2019 from a group at MIT where they actually demonstrated singlet fission on silicon and showed that this is going to be possible. So for me, the only thing stopping us being prevalent is all the other competing technology. I don't see any reason why this can't work, but we just got to get moving, yeah? Okay, so let's take a look at some of the progress. So this was a paper I was involved in where it was actually the first paper to put singlet fission material on silicon, but all of the advantages I talked about on a couple of slides ago were just not available because we actually used tetrazine as the whole conducting medium. So it was a completely different sort of device architecture. It worked, it didn't work that well, but it demonstrated that we could interact these materials with silicon quite effectively. And then we have the big breakthrough paper in 2019. Now the efficiency of the device wasn't fantastic, but this team is a team of organic optoelectronics researchers, and some of you may recognize this name here. Bowendi recently won, I think last week, won a Nobel Prize for physics for his work on quantum dots. And indeed, the likely reason he was involved in this work was because that is the other way to try and get triplet energy into silicon. It's to take that triplet energy, transfer it to a quantum dot, and then emit it into silicon. Okay, so this was a really exciting result, and it really showed that this could work. And there have been other papers that are showing that there are different sorts of ways to make this happen. But there are some really massive hurdles for our field. And I'm just going to talk about 3 of them now, okay? And then I'm going to talk about how we're going to solve them. So the first one is stability. All right, we want our cells to be at least stable for 25 years. Tetrazine is the molecule I'm going to talk about for most of this talk. It's not going to be tetrazine that goes into the field. It's unstable under light, and we tend to like light on our solar cells. So it's probably not going to be tetrazine. So that's going to be a big hurdle for the field. The other thing is this is coming back to those 2 stars that I put on a slide previously, where I said you can have 200% yield of triplets, but for how long? All right, so these triplets don't live forever. We need to get them to an interface, and we need to get them out. If you produce a singlet fission event and your 2 triplets stay together, they'll actually decay much faster than if you manage to separate them. So separating that triplet pair is a big deal as well. So that's something that we're working on as well, as a field and also as a research group. And finally, just talking about that device where we want our triplets to tunnel into silicon. We need to have our silicon device. Let's say it's a rear contacted device, and then we want to passivate the top layer of our silicon, obviously. And then we want to have triplets tunnel through there, but we have 2 competing things. Generally, if you want good passivation, you want a thicker passivation layer, but if you want something to tunnel, you want a thinner layer. So you have to balance those two things. But we are making really exciting progress there. So one thing to keep in mind when I talk about this being a tunnel contact, because I know we use that a lot in silicon already, is that we're tunneling an exciton. All right, so we're tunneling an electron and a hole at the same time. Right, so it's a two-particle tunneling event, which will have much lower cross sections. Yeah, so it is a little bit more complicated to get these triplets to tunnel into silicon. All right, so that's our 3 big hurdles. Now let's solve them. The first one. Now I realize that this, to a non-chemist, looks like you've been shrunk down on investigating a beehive, but there is a number of different molecules that are being studied and are particularly stable. And you may ask, well, stable for a molecule or stable? Well, stable, all right? They're in car paint, all right? So they're really, really stable, and if they're looked after better than my car, then they hold their shine for many, many years. So we can use these pigments. So this is a perylene diimide, and that is going into some of these sorts of car paints and lasting for many, many years. So these are stable materials, and they have been shown to undergo singlet fission. There is another class that we're also working on in our group that has particularly been used in Ferrari red. Again, a stable pigment. Yeah, so there are ways around this. The field moves slowly to this because tetracene and those sorts of molecules that are unstable are so well studied that when you want to try something new, you go back to the fruit fly before you move forward. But the field needs to move quickly to these sorts of more stable materials to make them work on silicon. And I don't see any reason why they won't work. So the second problem, as I said, was these parasitic decays. It's how do we make sure that the triplets get to where we want them to go, and how do we get them apart from each other before they decay? Yeah. Now this can actually be also solved synthetically. And now, so this was a piece of work that I did with my collaborators at Columbia University, where basically we had a singlet fission event occurring inside a single molecule. So you had, in this case, it was pentacene, which is this molecule here, and then it was bridged by different bridges, and then you had another pentacene molecule here, so that in one molecule, you create your singlet exciton, say here, and then you have 2 triplet excitons on one molecule. So we can actually tune the rate of fission by tuning the coupling between these 2 molecules, and you can do that by tuning what the bridge is made out of. So some of them are bridges, some of them are walls, and there is, I can't believe we got that through the editor, but some people tend to like walls more than bridges. Now, but that was a nice way of showing that we can speed up the rate of fission, right, by tuning that coupling. But we can also, I wasn't part of this work, but it's very, very cool, is that you can start to have polymers with pendants of fission materials. And then the triplets can hop away very, very easily, all right? And that's just driven by entropy. And you can make these molecules, they're macromolecules now, so then they become a bit easier to process as well. So that's a very exciting development. Again, though, you're facing the problem that the triplets may want to stay next to each other and then they would decay. Another paper I got the chance to be a part of worked around that, right? So again, just take a look at the purple versus the red molecules and know that the red molecule has a higher energy triplet than the purple molecule. If you have a singlet fission event here, the triplets will move to the edge of the molecule and they won't be able to interact with each other. So now what we're able to do is on an ultra-fast timescale, so sub-picosecond, generate 2 triplets, but then also have them living for many, many microseconds. So that was a really exciting result, because basically, in general, just notice that this x-axis is running backwards for some reason. In general, as you went to lower triplet decay rates, you had much slower singlet fission events, right? So where you want to be is up here in this top quadrant, and by designing these molecules where you have an energetic landscape, you can start to get these triplets to move apart from each other and actually have both fast fission as well as long-lived triplets. So there are synthetic ways around that second problem. The final issue is trying to coax these triplets into silicon. Okay, so how do we get that tunneling to occur? Before I get too far into that, I'm going to have to do a quick digression into how do we actually know we're getting triplets into silicon. As you may imagine, if we had something above 100%, I would have put that on an earlier slide. So that would be the best way to tell. If we have an EQE above 100%, we could say for sure, we're getting multiple excitons in at this wavelength, and then that's the end of our job. But that's not how R&D works, right? We're probably not going to get over 100% the first time we try and make a device. So what we actually do is we use the spin properties of triplets to work out whether triplets are making it into silicon. And to understand that, all you need to know is that after singlet fission, just forget about this state here, don't worry about that for this talk, you produce this singlet triplet pair, right? You got your two triplets, equal and opposite spin, net singlet state. If you apply a magnetic field, it actually increases the barrier to separating to your free triplets. And what happens is you end up going back to your S1 and you end up fluorescing light, okay? So as you increase your field, you get more photoluminescence from your singlet fission material. Because as you increase the field, you weigh the equilibrium, you put your finger on the scale and you weigh the equilibrium towards the singlet population, and that will give you more photoluminescence. Now the way the Baldo group at MIT used this is they showed that, well, okay, so the tetrastring fluorescence increases as field. There's nothing amazing about that. That's been known since the 60s. But the silicon photoluminescence was actually decreasing with field in exactly the opposite orientation, right? Following exactly the same sorts of trends. And that's because the silicon photoluminescence depended on triplets getting into the silicon, right? So because we have an increase in photoluminescence for our singlet fission material as a function of field and a decrease for the silicon, we can say triplets are making it into silicon. So that's the way that we are able to identify whether material is working, and then we can start to optimize. All right, so that we don't have to make a full device, make the EQE work. We can do this on an all-optical precursor and speed up that optimization. Now, I'm going to go into another lie in a little bit of a digression here. So I lied and I said that you produce a singlet state because it's forbidden to go to the other spin states, but then I also told you that forbidden things happen many hundreds of millions of times per second. So we designed a molecule a while ago that would trap our triplets next to each other, and the fact that you have this nice benzene ring means that the triplets will be very well coupled for a long period of time, and they remain coupled so long that the spin singlet was actually able to evolve into what we call a spin quintet. So instead of your triplets having spins like this, the spins were like this, okay? And that has absolutely no use for PV, but it was really, really interesting and it was an exciting result that we didn't completely understand. So then we went away and we did some theory, and this is Miles submitting his first ever paper. He did some theory here, and he showed that, well, if this bridge between our molecules is rotating, then yeah, we can work out a way that we produce these quintet states, these two triplets with the spins aligned. And then we did a little bit more work with real theoreticians, and we found a different way that this could happen from a theoretical standpoint. And then the really cool thing that we did was that we showed that experimentally both of these mechanisms for creating quintet excitons, these quintet biexcitons, existed. Again, no use for PV, and we didn't find a use for it, but this wonderful group in Japan then said, well, if you have a quintet overall high spin state that you can produce reproducibly, then you can transfer that spin to the nuclei of another material. All right, so if you transfer that spin polarization to, say, water, all of a sudden you can increase the contrast when you want to do, medical imaging or MRIs. Okay, so it's a very different use for this, but it's just kind of a nice story of how fundamental research can lead to all sorts of different avenues. And one final digression is, if you have 4 unpaired electrons all working coherently, then people start to think about ways to create quantum computers. So the same group out of Japan actually managed to have a coherent quintet state existing for many microseconds at room temperature, which is very exciting. But once again, in the organic world, we're decades behind the inorganic world, so I don't see that being a quantum computer, but it's cool. Okay, so that's enough of a digression. Let's just focus in on some of the nicer results from our lab. So as I said a couple of slides back, just remember the photoluminescence from silicon, if it's negative as a function of magnetic field, it means that triplets are getting into silicon via tunneling, and that's good. That's what we want. So we have The MIT group tried hafnium oxynitride, so we tried to remove the nitrogen and see if the oxygen worked. But for none of the thicknesses that we used, were we able to actually get that negative MPL. For this material, which I'm not allowed to tell you what it is, we were able to get a negative MPL at about 1 nanometer of thickness, but then that quickly decayed off, okay? So while it seems like an almost impossible task to try and create an interface that both passivates and allows for triplet tunneling, if you have the right if you have the right material, you can do this, and you can actually see that we have this exactly what we expect from a singlet fission generated triplet, helping triplets into silicon. So if you have the right materials and you have the right students, you're able to work out these interlayers and actually make sure that you can force the triplets to tunnel in. So we have this result, but we've tried many different interlayers, and we were able to show that actually for now 4 of them, 4 different types of passivation layers, we're able to allow triplets to tunnel in. And that's really exciting. Sorry, I should have mentioned, this is Alvin Moe. He's a PhD student who did all this work. Yeah, so this is really exciting because now we actually have some materials that we can go to much larger thicknesses, which will passivate the surface, but also allow for triplet tunneling. I'd really like to tell you what these materials are, but currently we're not allowed to, so I will reveal that in due time. Okay. So I hope that you've all learned a little bit about singlet fission and what I've been doing for the last 10 years. But I just wanted to take away a few conclusions, and then I'll wrap up. The first is that this technology allows us to circumvent most or many of the challenges of conventional silicon tandems. All right? Mechanically stacked tandems or monolithic tandems, they all have their own different challenges, and most of them have to do with the conduction of that top cell and or making sure that you current or voltage match your top and bottom cells. We can circumvent that, right? And that's really exciting, and that's why I'm excited about the technology, but it also is going to introduce a few hurdles, right? So I would suggest that we, as ARENA has done, invest in all of these technologies and see which one is able to, well, if it's just one or which many are able to win out. So we have these 3 big hurdles, but we have ways around them, right? So that first hurdle was stability. Now we have some people in the audience who are synthesizing materials for us that are suggesting that we can do singlet fission in really stable materials, and in materials that are so stable that they're used in car paints, right? So this is really exciting, and that's usually the problem. I can't see Richard in the audience, but every time I give a talk, he asks me how stable my materials are. So the one time he's not here. Anyway, so we have a way around this. The second hurdle was the fact that, well, we need to be able to manipulate the triplets so that they separate from each other, and we have a number of different design strategies to do this now. This is not, for me, it's difficult chemistry, but for a synthetic chemist, this is not that difficult. Okay, so you can start to design ways to make sure that your triplets get away from each other and then guide them into your silicon. And finally, that tunneling problem, which seemed like such a big problem, seems to work with a number of different materials. Okay, so this obviously needs a whole lot of optimization, but those of you in the silicon field may well know that you are constantly optimizing your passivation surface layers, so I don't think this is so different, right? So we've got to just optimize that. Yes, it's a balancing act between passivation and the efficacy of singlet fission, but you know what? I think it's still pretty exciting that we're going to get around them. So I would say that although we have 3 big hurdles, I think we have more than 3 solutions for these hurdles, so hopefully we can make that work. So with that, I'd just like to thank the entire Amiga team, of course, including our collaborators in largely, well, only in China, who are supporting our work, as well as ARENA for supporting both my fellowship and this current Amiga Silicon work, the Marie Curie Association for supporting some of the spin physics that I showed in there, as well as the Australian Research Council for my future fellowship, and thank you all for listening.
Thank you, Murad, for the nice talk. It was very informative. And we're kind of happy to complete 2 courses in one seminar, one undergraduate, one postgraduate.
Yep, sure.
In fission.
Yep.
So Any question from the audience?
Thanks, Murad. That was a wonderful talk. This ARENA-funded project, what are you promising to achieve by the timeframes of, the end of the project? Are you going to have a working cell with more than 100% EQE?
We didn't say more than 100% EQE. We said more than the base cell. So we want to see a positive effect, just because we don't want to tie ourselves to one silicon device. But yes, we have to see a positive effect in the next 2 years. No pressure. Yeah.
Any other questions from the audience?
Thank you, Murad. That was amazing talk. And I have one question, if it's not secret yet. What's the thickness, optimum thickness that you considered for the organic material?
Or for the organic material? So that depends very much on the triplet diffusion rate, length. So for tetrazine, we're finding around 30 nanometers is okay. But there are other materials, and again, we can design other materials that allow for further triplet diffusion, perhaps sphere energy sort of gradient. Yeah.
It was a great talk, Murad. Thank you. I learned a lot along the way. I'm interested when you're doing your optical assessments of the performance enhancements from the changes in the PL, what you know about converting that change to an efficiency change. So as you optimize around the PL, when do you make a device and look for that?
In parallel. So we're going to be doing, yes, so basically in parallel. We'll first get that so we don't have to put contacts on every device. But once we have that PL optimization, where we say that's a result, then we move to MPC, which is magnetic field dependent photocurrent. And if we see that same trend in the photocurrent, then we know that the triplets are being injected into silicon and also collected as charges. Yep.
And what are you expecting or hoping to see as a boost in efficiency? Because your target, your 41% is out there as a ceiling.
Okay, so I guess it would. It's always timelines, but I don't see a reason why we can't get over 30% with a very, very good bottom cell, right? So that's not my world. Yeah. So I don't see a reason why that can't happen, but it's always a question of timelines. But yeah.
Thank you.
Everyone here? Yeah. Hey, thanks for the talk. So do you think there would be an inorganic material with the same properties, or this is something that is exclusive to organic?
So multiple exciton generation occurs in inorganic quantum dots for a similar reason, right? Because you start to confine your electronic states, and then you have discrete energy levels, and then you're able to undergo multiple exciton generation. In most of those systems, they have heavy atoms, which means that spin is not a good quantum number. So there's nothing to stop that first. If you have, let's call it levels 1 and 2, you can have level 2 giving you 2 level 1s, but you can also have level 2 giving you 1 level 1. So that's the advantage over that, but there are many quantum dot systems that do this, and indeed silicon does this, I think, if you hit it with UV. Just the reverse Auger process, yeah.
Thanks for the great talk. I'm curious about the molecular changes being done to the organic layer. Is there some sort of understanding of the strategies, for instance, adding functional groups or adding more bulky groups that will hinder, and what are the expected effects of that?
Yeah, okay, so excellent. So the difference here, there are two things to consider. One's the central chromophore, right? So where most of the Frenkel exciton sits, and the other is how they pack. So first we'd focus on the chromophore by trying to find chromophores that are both stable and have, singlet energies about twice the triplet, and of course the triplet has to be higher than silicon's band gap to inject. And then if we have that, but they're not doing singlet fission, then you can start playing with the solubilizing group. So this Rylene and this Rylene will have exactly this, very, very, very similar absorption and emission characteristics and similar singlet and triplet energies, but they'll pack very differently in a crystal because we've got these extra groups out here. Yeah, so the strategy first, I would say, is to find the chromophore that's going to work for us, and then we can play with stacking and things like that.
Can you simulate the fluorescence spectra with doing some DFT calculations on different organic molecules and then trying to theoretically predict something?
Yeah, so there's a lot of work that's gone into that recently, doing that with sort of a machine learning algorithm to try and work out. A number of people are looking at whether, because it's not just that fluorescence spectrum, it's the energy difference between the S1 and the T1, and it's believed that the diradicaloid nature of the ground state plays a massive role in this, but it's kind of one of these empirical things that's been machine learned rather than underpinned by a solid understanding.
Folks that created the open source Orca software, they have a very good analysis on especially the fluorescence spectra. Okay. And I know the people that did the actual background writing of the code. It's super interesting, and it's open source, so. Yeah.
And perhaps we'll chat after. Yeah, thanks.
If I'm allowed a second one. Murad, thanks. I was wondering if all these different options of materials do you think they offer the same performance potential? Or are there material differences in the same way that, we're looking at perovskites, different outcomes for the different materials?
You use the word potential, so performance potential is the same. But no, so the paralenes, which are these guys here, the best yield I think I've seen is about 150% instead of 200%. So no, it depends molecule to molecule. But there's such a wide expanse of these molecules that haven't really been studied. So that I think that's one of the advantages that we're going to have now that we have a large team able to do this. But yeah.
Question about the exciton tunneling from one material to another. At the start you mentioned exciton's a bound beast in the molecular organic material, yep. And then in silicon it's a loosely bound, completely different beast. Yep. So you're not tunneling the molecule, are you? You're tunneling the exciton. So how does that work?
Well, an easier way to think about this is the way triplets move through a crystal material anyway. So the way a triplet goes from one molecule to the next is via tunneling. So it's actually, because there's essentially a potential barrier between each individual molecule because there are no nuclei around. So it's tunneling from molecule to molecule. Then when it gets to something like silicon, my best understanding is that it will tunnel in concert in a process called Dexter transfer. And as soon as it's in silicon, then that electron and hole don't know where they came from, right? Because your dielectric constant's so large that they get screened from each other.
What happens to the 1 eV difference in binding energy when it does that?
We've already paid for that. That's an excellent point. Yep, that's a great point. So, sorry, there should have been a fast. Yeah, the difference in energy here, right, is something like 2.9 EV. Help me, Homo and Lubo. Alex, you were looking at this. I'm putting you on the spot.
The silicon?
No. The Homo and Lumo for tetracene.
Homo and Lumo. Yeah, I think that's about right.
Yeah, so it's quite large, and then we say our singlet energy is 2.3. So when we're talking about our singlet energy, we've already paid for our binding energy. And then we say our triplet energy is 1.25 in tetracene, for instance. And that's well below the Homo-Lumo gap. So we've already paid for that energy when we're talking about triplets. Yeah.
Okay, let's send Murad again to the next talk.
Thank you.